Ooh la la. Right. All right. Guess we'll get started. Let's see. Oh, cool. Okay, so let's see, what logistics do I need to discuss? Homework, I guess, is due on Wednesday. Obviously, we haven't actually covered word embeddings yet. I think it's sort of doable. So, but again, you know, if you don't think you're ready to complete the assignment before the deadline, you know, just send me an email or something and we can work something out. Yeah. What else? That's about it. Okay, so I want to just finish off what we talked about, what we ended off on last lecture. One thing that I sort of sped over, and I think it sort of pays to think a little carefully about this, is, so, you know, last time we talked about this guy here as well, right? So like what we have here is some likelihood for a particular partition. This is the class-based idea. The thing I want you guys to think about is, what do these random variables correspond to, right? So here we have W, we have C1 and C2, right? Right, so what do these random variables correspond to? I think it's sort of easier to see it through this slide, right? So we talked about this point-wise mutual information, which you will be looking at in your homework. So maybe it's obvious to you at this point, but let's just refresh a little bit. So here I'm looking at the average mutual information of W1 and W2, right? So what are W1 and W2? Well, they basically correspond to this data set here, right? On the left-hand side here. So remember what I did was, we have our corpus, right? Again, just think of this as Wikipedia or some really, really large corpus of text, and I have T1 to Tn, or n is the length of my corpus, right? And then when I think about bigrams, what I'm really doing is I'm just creating data sets of this form, right? T1, T2, T2, T3, T3, T4, and so on and so forth, right? So you can think of this as sort of the data for a bigram model, right? And then what you're actually doing is the W1s, it's like you're essentially looking at a joint distribution where T1 and T2 are just basically samples from my W1 and W2, right? So that's really what, you know, when you're thinking about these random variables, W1, W2, that's what you should be thinking about. Like in this case, W1 just corresponds to, you know, sort of the sample, the unigram version of this corpus. And so, ends up just being the empirical distribution of the words, right? But what's interesting is that when you have W1 and W2, then it's, then what you care about is sort of the correlation between these, right? So even though W1 and W2 themselves are very, very similar, right? Where you get the interesting relationship is from the fact that, you think of this as W1 and W2 as a joint distribution, right? And so what you care about is the sort of this co-occurrence of W1 and W2. Okay, so that's, so when you think about these random variables, like in your mind, you should be thinking about basically the data you sort of extract from these corpuses, and they come in this form. Okay. So then I mentioned this pointwise mutual information, which you guys will be covering in the homework. Here you're basically, this first thing here is a sort of an average effect, right? So this is a summation over all possible word pairs. I do these calculations. Here, this is for a particular word 1 and word 2. You can then calculate these probabilities and then calculate this pointwise mutual information. And then in your homework, you can see how you can actually use that as a sort of a proxy for like co-occurrence. Okay. Right. So yeah, so we're going to finish off language models, which basically steps right into word embeddings, as we'll see in a little bit. And so the key point of this is that, I've said this, I guess, many times now, we're basically going to represent words as vectors in RD, right? So D is going to be some, wouldn't call it a parameter, but like usually you think of D as like 300, right? So you're going to represent all the words in my vocabulary in this 300-dimensional vector. And the idea is that hopefully the geometry of sort of these word embeddings, that's what they're called, sort of the relationship between them in this high-dimensional space actually captures something interesting about the words themselves. Okay. So yeah, so basically it ends up just being like a really, really big logistic regression. I think it'll be clearer how it ends up being a logistic regression in a little bit. But remember, what is a language model, right? We're trying to just predict the next word. But what is a prediction of the next word? That's just you're assigning a probability to my vocabulary. So that's just the same thing as, remember, with topic models, it's like a topic is a distribution of words. Here, I'm just assigning a distribution, a probability to all the words that I think are going to be next. And so it's really just like a logistic regression, right? Logistic regression always going to be a multinomial logistic regression, but it's still the same idea, right? It's like you're just predicting probabilities ultimately. So you can use sort of, or we're going to use logistic regression basically as sort of the fundamental model behind all of this. Oh, and, with a lot of different things to make it actually not just a logistic regression. Okay, and the other thing is that we're also just going to use stochastic gradient descent because it's going to be a really complicated model, and it turns out stochastic gradient descent really works really, really well with these types of things when you have a huge data set and you just, yeah, there's no like, closed form solution to any of this. Okay. Anyone have any questions? I assume not. So the idea, so this is going to go back to that intuition that we had before. So we sort of tried to use this intuition to guide our notion of like the class-based language model. It's going to be the same intuition here, right? Which is that like what you want is, suppose you have, suppose in your corpus you had the first sentence, which is the cat is walking in the bedroom, right? That should basically, the idea is when you're looking at your corpus, what are you trying to do? You're trying to find sequences of words or sentences that appear that tells you that this is a valid sentence and you should upweight it in your likelihood, right? You want to upweight the sentences that appear. So you want a model that basically agrees with what you see in the training corpus, right? So that's the intuition. And then the next intuition is that like, well, okay, so suppose I only see this first sentence in my corpus. I want my model to be flexible enough to basically sort of, allow it to sort of give, allow it to divert some probability mass to these other ones as well, right? Because, due to the fact that these sentences are somewhat synonymous, cat, dog, walking, running, whatever, somewhat synonymous. The idea is that if I see the first sentence, I want to obviously upweight that particular sentence, like, the likelihood I assign to that particular sentence, but I also want to give it some, some mass to the other sentences that are basically the same thing, right? And so what we're going to do, in the class-based model, what we did was, well, let's just say, okay, if I sort of, squint my eyes a little bit such that cat and dog are sort of similar, then I'm going to group these sentences together so that then they share the same probability, right? Now what I'm going to do is, you can sort of think of it as like, here I have some words and I'm trying to predict the next words, right? So it's just the whole language model. And you can think of these words as like parameters, right? And so I'm going to say, I'm going to represent, this cat with some, let's call this, v cat, which is in R to about 300, right? So this is now going to be a 300 parameter. So for each word, it's like I attach each word 300 parameters, right? So these 300 parameters, basically you think of it as some point in some space, right? And I have some huge function that sort of takes in these points in this high-dimensional space, and then spits out a probability, right? And so because my function is sort of, is somewhat continuous, what that means is, if all other parameters are the same in my model, except I replace cat with dog. Now, if cat and dog are in, the same vicinity in my high-dimensional space, then that means that my probability that I assign to this sentence shouldn't change too much when I change the word cat to dog, right? So somehow the fact that I'm going to learn this continuous function of the parameters, and these parameters are basically going to be, this high-dimensional vector, which is also going to be continuous. The idea is that I can then sort of, hopefully what my model is going to do is going to learn this this function such that it's going to realize that there are certain words that if I put them in the same location together in this high-dimensional space, then that's going to make it easier for me to predict, define a word, which is basically saying I can then sort of assign the proper likelihoods to sentences. Okay, so anyway, so that's sort of intuition. Let's go into the math. I think that will be sort of the second piece of this puzzle here that sort of makes this a little bit clearer. Okay, so I like to, show this diagram first, just because it's freaky looking and should be completely not understandable. So this is the language model. It's called a neural language model because it takes sort of inspiration from these neural network architectures that we're going to discuss later on, right? The key point about a neural network is that you have this nonlinear component, which is this hyperbolic tangent, which we're going to look at in a little bit. But this is really complicated. So what I'm going to do is I'm going to start simple, and let's look at a very simple neural language model that sort of starts with the most basic but really important aspects of this model, right? Okay, so what are we doing? We're going to focus on a bigram model, right? What's a bigram model? That's when you only look at sort of the previous word, right? And so here I have this bigram model, and essentially what I'm going to do is I'm going to basically do the softmax thing that we've talked about, a million times, right? So this is my softmax I mean, okay, at this point, I've forgotten if we must have talked about this, right? Softmax. Yes, if yeah, and now I'm
Can you go over
now
one,
the years.
even if we did?
Sorry.
Can you say it again, even if we did go over it?
Oh, okay. Sorry. No, I actually think maybe we didn't. I just the classes have blended in now, so I have forgotten. Right. Okay. So what do we do? So my point is that what we're doing is this is sort of the whole logistic regression point where, like, suppose I have a linear model and okay, so let's be a little bit clear here, right? So usually we have this linear model, y equals x beta plus epsilon, and the key point is that this y, if you don't do anything, is going to be in R, right? Well, R to the n or whatever, so not important. And so what you want to do is you want to be able to convert to your y's into the 0, 1 domain, right? Because you want it to be a probability, right? So this is how you get from like a normal linear regression to logistic regression, because you want to do a classification and you want to do assignment here. So then what you do is you do sort of softmax of y, which then allows you to convert something from R to 0 to 1. So basically, this is the softmax layer where what you're doing is you have some y, right? This is going to be in R to the v, right? V is your vocabulary. And what you want is you want to convert this such that it becomes a probability distribution, right? So then what you do is you basically, convert it to, you look at this guy instead, right? So now each entry is going to be e to the power of y wt. Well, okay, so I could be a little bit clearer here. So let's look at y1 all the way to yv, right? Then this is going to get basically, to convert into a probability distribution, it's going to be e to the power y1 over sum over y's, e to the power y2 over sum over y's, and so on and so forth, e to the power yv over sum e to the power yv, right? So this is my original y vector, and I want it to be a probability distribution. So then I do this transformation, which is basically it's called the softmax transformation. You do the component wise, and then what that means is that now if you look at this, obviously this vector is such that they sum to 1, right? I mean, that's just the way I've just set this up, right? Okay, so actually, so softmax is pretty important to remember. We're going to use this a lot. Something which I may or may not have mentioned before, when you do things like multinomial logistic regression, if you go back to our notes, what some caveats that we always mention when you do these types of things, that like, well, I only actually need to specify v minus 1 of the parameters, right? Because then once I specify the last one, they sum up to 1. So then you don't need to, you just do 1 minus the rest, right? So if you remember, I mean, even with logistic regression, right? Logistic regression, I only need to just do one of them, because then the other probability is 1 minus that, right? Okay, so the one I'm about to talk about is somewhat of a subtle point, but in machine learning, basically, like, you don't care. Like, you don't actually do like 1 minus the rest here, right? So here usually, if you were being proper about it, you would just do 1 minus I guess 1 minus the rest, where the rest is like the sum of those, right? So then that they just sum up to 1, exactly. Because then otherwise, it's as in you're sort of over parameterized, and so your model is a little bit silly. The thing is that with machine learning, these types of applications, you don't really care that they sum up to 1 that much. Like, it doesn't have to be that exact, partly because my v is just so large anyway, that just sort of caring a little bit about the fact that they sum exactly to 1, and caring a little bit about the fact that I have more parameters, I have more variables than I really need. It's just not worth it. So when you look at the way we do these things in machine learning, you actually just have one of these altogether without worrying about the last variable. Okay, sorry. So that's not particularly important. Just something to note. Okay, so what? Okay, so what are we doing? So we have a bigram model. I'm trying to assign a probability to seeing WT, right? So as an example, let's say WT, right? So let's say WT minus 1, WT was like cat and then sits, right? So first of all, like in this particular case, I'm going to look at one particular word, right? So here this would be sits, and this is conditioning on the previous one being cat, but obviously, this is going to be one particular probability, right? But then you obviously have to define it for all possible words that follow the cat. Okay. Okay. So what are we doing? We're trying to define a model for assigning probabilities to words in this bigram model. Let's just go through this guy here first. Okay. So how are we going to do this? Okay. So maybe if I add a page here, because I'm getting a little bit messy. Oops. Okay, so the model works basically as follows, right? So what you have is you have this C. C is okay, so there's the question, do we use e to the power of YWT instead of the pure frequencies YWT because we want to avoid degeneracy from frequencies of 0? Or is there another reason to use the exponential function? So, oops. Where did my thing go? Yeah, so here, I think you should just think of this in terms of the fact that my y is going to be, like, I have no restrictions on my y. So it can be anywhere from the -infinity to infinity. And the e to the power basically sort of squeezes it to 0 to 1, and so you sort of like it's sort of transforming it into the right space that you care about, right? So this is sort of the same thing as basically what we're doing whenever we do logistic regression, right? Yeah. Okay. So yeah. So you should think of these y's as just like basically like big numbers or small numbers or just continuous numbers. All right, so how is this going to work? Basically, what we're going to do is we're going to set up this C matrix, right? This C matrix is basically the key matrix that we're going to do, going to have, and it's going to look like this. So it's in R V to D, right? What that means is, here, each row, right, corresponds to sort of the word embedding, right? So each row is basically the word embedding that we've been talking about, right? So how I said, I'm going to represent every single word by a vector in RD. This is basically C is just a stack of my word embeddings. If you've done the homework or you sort of play around with the homework, this is basically the output of your embedding model, right? So every single row corresponds to a word embedding. And so when I say C of W, I'm basically saying I want to basically extract the row that corresponds to the word W and I want to get out that vector. Okay, so does everyone understand what C means, right? So C is V to the D, and V here, you can index it by just the number, but you can also just index it by the word, right? So here, let's think of cat, the word cat, and so then this is C of cat. Okay. So is Y not an indicator for a word in the vocab? I haven't explained what Y is yet. It is not that. So okay, so let's go slowly. I think it's a little there's a few things going on. Okay, so C, so far this is C, right? And then what happens is I'm going to then define X to be C of WT minus 1, which in words is basically the word embedding of WT minus 1, right? So for this particular example, I said WT minus 1 to be cat. So this is the cat word embedding, right? So X, you can think of it as in R D to the 1, something like that, right? Then what I'm going to do is I'm going to have this, basically it's like going to be a linear, this part is a linear regression-ish type part, right? So I have Y equals to B plus AX. Well, A then must be R to the V times D, and B must be R to the V times 1, sort of. Okay, so so now let's think about how this all works together, right? Basically what happens is Y is going to be, it's helpful, it's important to write this out. Y is in R to the V, right? So R is a V-dimensional vector, and basically what Y corresponds to is the probability you assign to seeing WT. Okay, because think about the way this works is you really have sort of, it's a little bit like having one parameter here. The one parameter here is your WT minus 1, right? So that's cat, right? So what I'm saying is I want to say, given cat was a previous word, how am I going to assign the probabilities for the next word, right? In particular, what I want to care about is, I want to know what probability I assign to sits, but actually in order to calculate this, I need to assign probabilities to every single word, right? So really what we're looking at when I say Y is I want to look at the probabilities assigned to every single word. In order to do that, it's going to be the same thing as we do with logistic regression. You first start with a linear model, right? So we have our X that corresponds to the word embedding for cat, right? Now I'm going to hit that with a matrix A, such that A obviously parameters of my model, and then what comes out of that is going to be a v-dimensional vector. Then I hit this with a bias term, and then finally I get the Y, right? So Y is a vector of numbers of length V, such that each entry of it corresponds to the pre-normalized, you can think of it as like the score you assign to the WT attached to that particular entry, right? So, sorry, I was doing it in some space. Y, it's going to be this vector like this, right? It could be like 34 point whatever minus 200, blah, 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 right? So some number. But in particular, what I care about is I'm looking at the WT row, which in this case is sits, right? So let's suppose this number was 32.1, right? So what is this number? This is basically the score of how likely I think WT is going to be, the word sits comes after cats, right? So then once I have this vector, then I sort of do, this is basically the softmax transformation to then turn everything into, point ones, right? 0.2, blah, 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 blah. And so then finally, if I look at sits, this is going to be 0.003, for instance. So that is exactly what comes out of this probability. Okay. The funny thing is, this is actually like the simplified model. Okay, questions. If there are no questions, I will scream and shout. No, I'm not going to do that, but there must be questions. Oh no! Oh my god! Oh. Okay. Question 1, is the training data for why the word context counts? Is it training data for why? Okay, so far I haven't actually explained anything about training data, right? So all I've done is set up a model, right? I think for now, I think that's actually forget about the training data. The training data will end up being the WTW, WT minus 1 WT. That's my training data. So so I think actually you should just think of this as a model. It's like a very fancy logistic regression. So we need to understand the model first before I explain to you how to actually fit this model. Okay, so what is Y? Okay, so what is Y? Okay, so there are many layers of that question. Basically, what Y is, intuitively, what Y is like when you do logistic regression, for instance, you're given covariates X, you do some, you hit it with something, blah, 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 and then you get out this Y. That gives you basically the score that you then assign to your classes, right? The whole point of logistic regression is, given a set of covariates, given information about an individual, how am I going to classify it, right? And the way the logistic regression works, as I sort of explained in class, it's basically like linear models plus a softmax, right? So it's like you fit a linear model first, right? You have some linear combinations of the covariates, and that gives you a score, but that gives you a score for each of the possible classes that you're going to predict. And then you do a softmax layer such that they sum to 1. So then you get basically a probability that you associate with every class in your classification problem, right? So this is basically that in an extreme form, right? So what are we saying is that, basically, given the previous word cat, I want to, my model wants to specify the probabilities that I'm going to assign to the next word, right? So what that's going to do is that basically I start with my word cat. I then look at the word embedding version of it. I then hit it with this matrix A. This matrix A actually contains quite a lot of information, but just supposes some set of parameters, right? And then once I do that, that gives me out my vector Y. And the Y is equivalently going to be the score that I assign to each word that I think will be the word after cats, right? Because the whole point is I'm trying to create a probability distribution over my vocabulary, which corresponds to what I think the next word will be after cats. Okay, so then the Y is the pre-normalized version, and then once you normalize it, that's exactly what this expression here is. Okay. So another question, why are A and C different embeddings? Oh, good question. Yeah, that is a good question. So actually, when we look at word embeddings, which is the sort of the next topic, or like, yeah, when we do word embeddings, you actually use the same embedding. But in this particular case, we're going to be a little bit more general and assume that the embedding you care about for the words that you're sort of like, you're conditioning on is going to be different from the embeddings that you care about for the word you're going to predict. Why would you do that? Like, it seems like, yeah. So the way they set this up, when they first thought of this model, like they just wanted to be as general as possible. And then the argument, I mean, I don't think there's that good of an argument, but it's better to be general. And then, if it's the case that the embeddings you learn are basically the same, then you can basically replace it. So basically my answer here is that intuitively, I think it is sort of silly to waste that. You should really just have one word embedding for your words. But this was sort of the first model and they wanted to be as general as possible. But as you keenly pointed out, it is somewhat redundant. And in fact, that's what we do for word embeddings. Okay, sorry, like word embedding models, so this is a language model that uses word embeddings. In order to create the proper word embeddings you do in your homework, it's going to be different from this model itself. Yeah. But actually, yeah, so that is a good point. So because if I write this A in this form, it doesn't look like an embedding. But once you restrict it to a particular index in my vector, then you realize that actually A is just, again, going to be like a word embedding, right? Because here A is V by D. C is also V by D. Well, maybe you have to get the matrices aligned up the right way. But yeah, so A here corresponds to word embedding, but it's like a different word embedding, and it corresponds to the word that you're trying to predict. Okay. Good point. So any more questions? Because I'm only going to make this even harder. And I will talk about training in a little bit because I think that's also very important. But for now, like, what I want you to sort of realize from this is that this is really not that much more difficult than what we've been talking about when we talked about linear models, logistic regression, right? This is almost the same thing as logistic regression, except I'm being a little bit cute about my X, right? You're basically like, your X is this, like, here, remember, okay, X corresponds to C, and C is this humongous matrix, right? So what you're actually going to do is, this is actually a parameter that you're going to optimize over. But like, besides this fact, it's roughly, it has the same feeling as a logistic regression problem. And if you go back, into your, your notes, you can see it really is basically the same thing, right? You have this, this Y, it's a bit like X, X beta plus epsilon, but not really. And then you do a softmax layer, and you then get your probabilities up, right? So it's like classification, right? You're doing classification problem, except I'm doing this really high dimensional classification problem. And I'm also being a little bit weird about how I share my variables around, how I share my parameters, okay? But like, it's sort of like, yeah, it's just like logistic regression, but just fancy logistic regression. Okay, so now let's look at the more extreme version. Well, I mean, I wouldn't call it that extreme. So essentially, I mean, really, this is not actually that much more difficult. There are sort of two pieces of this puzzle that are different. The one thing that's different is I actually have this nonlinear function, right? We're going to basically introduce a nonlinear function. And then the other thing is that, well, we're also going to not just have a bigram, but like care about like my n-gram. Okay. Everything else, so I actually don't think this diagram is particularly informative. We will go back on this diagram once we sort of described the more general model. But here for now, let's just, yeah, the two main differences to make it the general neural language model, which is from the paper by Bengio, it's basically adding a nonlinear component and extending this to n-grams. So let's see how we're going to do this. Okay. So this part, same thing. I have softmax of my y to get this vector. This then gives me a distribution of over my vocabulary such that I can then predict the likelihood of WT given the rest of the words. Right? Now the difference comes in this, how do I actually generate my y's now? Okay, so this is going to be a little bit more annoying. I think it always helps. So this is, just words of wisdom, not really. Sometimes if there's an equation and you're like, want to know what's going on, the first thing you want to do is always just assign dimensions to everything. For some reason, it just really, really helps with like your own thinking. Okay. So let's think back to what we had C. Remember, is that matrix with V by D. So C is in R to the V times D, right? So that's important. So that's sort of this is like the key thing you're going to learn. This is your word embedding matrix. Okay, so then what is X? Well, first of all, what is C of WT? That's T minus 1, doesn't matter. That's going to be R to the D by 1, right? Basically R to the D. Here, what is X? This is actually just like, it's concatenation, right? So what does this mean when I take this brackets? I'm actually going to concatenate my word vectors together. So then what that gives me is X is actually not just R to the D, but it's R to the D times n minus 1, because there are n minus 1 embedding vectors. So this is D times n minus 1. So this is not going to be a matrix. Well, it's a vector. I'm just going to write it times 1. Right? So this is a vector where basically, put the word embeddings of the previous n minus 1 words. I'm going to put them next to each other. Right. So bam, 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 bam. I'm not going to put them into a matrix, so that's why it's just a really, really long vector of length D times n minus 1. Okay. So this is that's sort of important to know. That's how you that's how you generalize from a bigram to an n-gram. Your X is now just going to be a larger vector. Okay, so that's X, right? Where does X come in here? That's really basically, I have my indices that gives me the word embeddings, and then once I have the word embeddings, I'm just going to concatenating them together to make X. Okay. Now what do I do is, well, there are two things you can do. One thing, you can just basically, one route is just to go what we had before, which is y equals to b plus ax, right? That was what we had before. Remember, you started with your x and you hit it with b plus a. But now I'm going to actually add a linear component, a nonlinear component, where I have the same like b plus ax, but now it's going to be d plus hx. And I'm going to hit it with a nonlinear function. And then I'm going to also hit it with a u. Okay, so let's see how this works. This first part is obviously going to be the same as before, because remember, y is always in r to the v, because that's going to give me the score I'm going to assign to the word I'm going to predict, right? So b obviously also in r to the v. X, remember, is a bit weird. It's in r to the d times n minus 1 now. So then a has to be r to the v times dn minus 1. Okay, so that's how you get it to be a v vector. This part is also going to be a little bit weird now, because what I'm going to do is this step here, I'm going to actually set this up so that you have, so there's going to be sort of h hidden units. So I'll explain this in a little bit. So essentially what you want to do is you want to basically push this into h, and then you hit it with a hyperbolic tangent. So what you're going to actually have here is that I want this vector to come out to be r to the h. So instead of pushing it to r to the v, I'm going to sort of squeeze it to r to the h first, and then push it to r to the v. Okay, so how do I do that? I basically set d to r to the h. I set h to r to the h times dn minus 1. Right? So then this guy still is r to the h times 1. And then I do component-wise hyperbolic tangent, right? So every entry of my vectors, and I'm going to hit it with the hyperbolic tangent. And then finally, I hit it with u, which is then going to be v times h. Okay, so this d in d plus hx is not the same as the dimension d. No. So no, the d is the same. Yes, this is the same dimension. D plus hx. Sorry, what did I write? D plus. Oh, sorry, that d. Sorry. Oh yeah. No, sorry. Yeah. Sorry. Okay, you're right. Sorry. Yes. We should call this something else. You are absolutely right. Yeah, because it's not actually that important. Let's call this
Delta, maybe?
Delta. Oh yeah, good idea. I'm really bad at coming up with things. Okay, this is delta. I'm sorry. Delta. Okay. Yes, there we go. Sorry. Okay, yeah. So in neural network languages, like this is known as like the bias term. Basically, it's like yeah. I mean, okay. It's known as the bias term. We won't care too much about it. It's just basically a constant you add to it. Okay, so let's see intuitively what's going on here, right? So the key point again is this x. X is basically all the information I have about the previous words, right? So what I'm doing is I have my previous n-1 words that I'm sort of saying, given these words, how am I then what's my probability of predicting the next word, right? So what I do is I take these n-1 words, I push them into my high dimensional embedding space. So now I have this x, which is a concatenation of these n-1 vectors, right? So I'm concatenating them into this really, really long vector. So that's really, you can think of it almost as like the input, right? X is like the input. right? Now I want to, given this input, I want to predict, I want to assign probabilities to the output, which would be the final word, right? So then what I do is, one way I could just go straight and just do a linear, like, it's like a linear logistic regression thing where I just hit this X with B plus A. So that's my first component. Now I add this new nonlinear component, and I will explain why we add this new nonlinear component in a little bit. But for now, let's just assume I have this nonlinear component. So what I'm going to do is I'm going to basically do the same thing. So I have this X, and I want to push it into a different dimension. Right? I'll push it into H, which is like, you can think of it as like the dimension of my hidden layer, right? So I'm going to push this into a different dimension, and then I'm going to take a nonlinear transform and then push it back into my into what I want, which is a v-dimensional vector. Okay, so you can sort of think of it as like squeezing your data into like a bottleneck, right? So H obviously is going to be much smaller than V, right? V is 100,000, 20,000, 50,000, whatever. It's really, really big. H could be like 1,000, right? So I have this really, really large vector. I'm going to basically project it into a smaller dimension. So it's sort of like, ideally what you want your projections to do is you want your projections to like, compress your data. You take a nonlinear transform and then you project it out such that it sort of retains as much information as you can, but and then you just add it onto the normal logistic regression, which we showed in the first easy model, and then that's your final output, your y's. These correspond to some numbers in R, and then you do the softmax to get you a probability distribution. This is intense. Okay, so is this process similar in fact to using SVD and then dropping small singular values? So it's a little like that. I mean, it's not particularly so. This thing I was talking about, where like I'm squeezing stuff into this hidden layer, is really just intuition. SVD is sort of, SVD is basically like dimension reduction. You're sort of, what you're doing is you have your model, you have your data, and you're representing it in a low, with like less information because you think there's redundancy. It's sort of like that, but it's very sort of like that. But I don't think it's that good of an analogy, so I don't want to say you should do it like that, because SVD basically corresponds to like, just looking at the eigenvalues and eigenvectors and then that decomposition. Here, what we're going to do is the projection corresponds to some parameters that we're going to learn. So that's why it's a little bit different there, but maybe at a very, very high level. Okay, so yeah, so this makes me feel a little bit like topic models all over again, because all I've done here is just describe the model. All right, I haven't described how we're going to learn this. I haven't even like sort of been clear about what are parameters here. So that part is going to be important. Okay, so another question is it more like defining projection matrices as we transform from one space to another? Yeah, yes. So it's sort of like that as well, right? So H is basically a projection matrix into like H, into like little h, right? The key point is that like the projection matrix is going to be learned. Okay, so I think if there are no more questions, if there are questions, like, please ask me, because I'm just going to go through this slowly. And I think there are it's just like with everything we've done, there are a lot of moving parts. What are the variables here? Sorry, what are the, okay, so let me first just finish this thought. What are the parameters? basically the parameters are everything almost. So let's see. So C is my parameter, right? Through C, then X is sort of like a parameter, but it's not really. X is a parameter insofar as C is a parameter. H is a parameter, delta is a parameter, U is a parameter, A is a parameter, B is a parameter. Okay, so these are all parameters, right? So when you think of linear models, beta is a parameter, and that's it. Here, every single thing that I've highlighted is a parameter. Okay, so questions. Does the nonlinear component gather some information about higher order structure of the embeddings? So hard question. I wouldn't say it like that. I think the way I would say, like, oh, right. So I was gonna explain why we have a linear, why there is a linear, nonlinear layer here. Basically, the idea here is that nonlinear is going to be more general than linear, right? When I do linear regression, I'm going to learn a linear function, right? You know, x beta plus like x beta, right? But okay, sorry, I always like to just say things in, right? So usually what we have is we have x beta, and that's going to be my linear model, right? So y hat equals to x beta hat, right? Alternatively, a nonlinear thing, you know, is general, would just be like f of x, right? Some f of x, and I'm trying to learn the f, right? And so the general intuition is that having a nonlinear function just makes your possible function that you're learning just so much more general than not, right? Because if we go back to my first example here, right? This is learning a linear function sort of x to y, right? And okay, there's some caveats. Obviously, it's not really like that, but this is, you know, almost think of it as like I'm just learning a linear functional from x to y. Whereas if I do this, now I'm not only learning a linear functional, but I have a nonlinear component. What that means is that like it then sort of means that the function I'm learning can be more general, right? So we don't really understand what these nonlinear things actually do, but the gist of it is that we want the class of possible things we learn to be more general than just linear functionals, right? Because it's, you know, so in that case, why retain the linear component at all? Good question. Here, it's partly because maybe this nonlinear component, because I'm actually like projecting it down to h, right? So remember what I'm doing is I'm sort of squeezing this as well. So here you sort of like don't lose anything out, right? So I start with my linear component, and I have this additional nonlinear component, which would maybe get me like a little bit more gets me something more interesting in terms of my function I'm going to learn. But if I just restricted the nonlinear component, because I'm squeezing all this information in, maybe that's actually not as good, right? So generally speaking, usually what you do is you'll have both a linear and nonlinear, so that at least you know you're going to be as good as a linear, right? If you just have a nonlinear versus, well, okay, it depends on the way you set this up. But in this particular case, the way we set this up, you know, because we've sort of squeezed everything into this low dimensional space, and I do a nonlinear transform, I might not even do better if I just have that, right? So here I'm sort of being a little bit safe. I still stick with my linear component, but then I add this nonlinear component such that it allows my model to be a little bit more expressive. Yeah. So okay, so my answer was more at a high level about linear versus nonlinear. In this particular example, because of the way this is set up, because the fact that I'm, pushing everything to a low dimension, it's not the case that a pure non-linear thing is going to beat a linear thing. Okay. Also, so there are many sort of side comments to make about this. One comment being that this is just incredibly ad hoc, right? I'm trying to give you reasons why they did this, or reasons for doing this, and like, I'm trying to explain, blah blah blah, but really, like, there's no good reason why we should do this, in the sense that, like, there's no principled reason, like, there's no theory behind this. It's just, hey, I start with a logistic regression. Well, what's the harm in adding a nonlinear component? I'm not going to do any worse, right? So I'm gonna have a better model. It's going to be more expressive. There are more parameters, So really, like, it's sort of like with machine learning, it's like a completely different philosophy. It's like, let's just let's just add a bunch of stuff and then see what sticks, right? Because, like, all I'm going to do is I'm going to run stochastic gradient descent. If I run it for long enough, it doesn't matter. Like, these parameters will eventually do something nice for me, so that, like, even if this nonlinear component doesn't do any better, I'm just going to throw it away, right? Or maybe the U actually has, like, it's like actually not, that term ends up not being very useful. I will say as well, when you do word embeddings, you do exactly that. You throw away the nonlinear component. So in this classical neural language model, they try to make it as, like, complicated. I wouldn't say as complicated as possible. Like, obviously you can make it more complicated, but, like, it's pretty complicated. And you could argue that certain aspects of this are redundant or not necessary, and you would not be wrong. So when we look at word embeddings, you'll see exactly, like, sort of what's the bare minimum you need to get something interesting out of this. Okay. Any more questions? Okay, so let's so remember what we're doing. We have a model. This is blah blah blah, that model. Then what we have is we have parameters, right? So the parameters I specified in the yellow highlights. Then what I'm going to do is I'm going to basically run stochastic gradient descent. Okay. So then we need to think about how that actually works. Okay, so, well, this was done that already. Oh, yeah, okay, so hyperbolic tangent corresponds to this. You could ask why we do this, why not that. Mainly, it's like the classical reason. Nowadays, people use different nonlinear activation functions. We won't go over this now because it's not particularly important to this particular topic. But yeah, so this is just a nonlinear transform we want to use that works decently well. Okay, so basically what we're going to do is we have these model parameters, right? We're going to put them all into theta, right? Then I'm going to basically run stochastic gradient descent, right? And so let's think about how this works. Remember, with stochastic gradient descent, I look at one data point at a time. Well, what is one data point at a time? That's basically one n-gram, right? So remember the way I wrote this. Well, it's gonna be a little bit weird now because I have n for n-gram. Let's say T1 to TT is just my corpus, right? So then what I do is I'm gonna basically take some n-gram as part of my corpus, and that's basically one data point, and I could just go through this sequentially through my data, right? So the first one would be T1 to Tn. That would be my n-gram. that would be one data point. Then it would be T2 to Tn plus 1. Right. So that's a data point. And then what I do is I basically calculate the derivative of the gradients of the, sorry, I calculate the gradients of the likelihood, basically given by that expression, which then you have to calculate from the one we had before. Okay, so basically I have my model, and remember, this is like the nice thing about like these nowadays. Once I have a model, once I'm able to define a likelihood, here I'm trying to basically maximize the likelihood, right? So this is not like I'm minimizing a loss. What I'm trying to do is I'm trying to maximize the likelihood of the training text that I see. So I'm actually doing gradient ascent. So I'm trying to maximize versus minimize. Not that important. If your I1's not working, just replace plus with minus. But so basically what you're doing is you have this logistic, you have this likelihood function, which is going to be a function of all your parameters, blah, 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 blah. And then you're just going to take your derivatives with respect to those parameters, and you basically run stochastic gradient descent. Does that make sense? It's sort of weird because, you know, I'm obviously being very hand-wavy about, you know, how I can calculate this derivative, blah, 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 but like intuitively, it's really just stochastic gradient descent, right? Except the classic thing we did was we had a loss function, and, you know, loss function that could, you know, have a regularization term maybe or not, and then you take the derivative with respect to the parameters. Here, what I have is a likelihood function, and then I'm going to take, and usually with my likelihood function, I'll actually have a regularizer as well, but I take the derivative and I do the same thing.
Theta, though, has like a bunch of components. So its derivative is a gradient or a vector or something. So, I mean, when we did it before, we just did like a one parameter gradient descent, I think. So how does that change if we have like a bunch of different parameters, I guess? Like, how do we differentiate with B and A and U like all at the same time, I guess? Especially when A is like a matrix kind of thing.
Yeah. So yeah. So you would, I mean, you would basically do this. I mean, you can do it a few ways, but like you could just do it like for each particular component of it. So then you would update it. Okay. So you could do it in the sense of like, let's do delta partial likelihood over partial A. So you would just like change A, and then you would change B separately, blah, blah, blah. So I mean, we did this, like, we did this with the logistic regression as well, where like, because you have multiple, I mean, you have a vector, so you can look at it component wise, you could look at it vector wise, but it's basically going to be the same thing. So you could think of it as like taking derivatives with respect to particular parameters in your parameter set here. So I would update U, I would update A separately, I'd update B separately. Does that make sense, right? So I would, you know, then let's replace theta with like, well, just do it, sorry. You know, so I could start by replacing theta with B, and like take to it, well, that would not be with B. Then that would be update for B. I could do the same thing for A. This is just a sort of a shorthand way of saying I'm going to run stochastic gradient descent for each particular parameter, for every single parameter in my model. And when we then do like neural networks, you'll see how to like set this up when you have like matrices. It ends up being like matrix derivatives, but it's the same thing as if you were to do it component wise. So it ultimately doesn't really matter. You could then just say, well, how do I update Uij? Then I could take derivatives of the likelihood with respect to derivative of Uij, and then blah, blah, blah. But yeah, so like, yeah, so ultimately, like usually when I think about this type of stuff, I think of like parameters as just like, I mean, in some abstract sense, I just think of them as just parameters, and I'm taking the derivative with respect to parameters. Taking the likelihood with respect to the parameters because I want to, maximize or minimize them, and so I want to find the choices of parameters that move me in the right direction. The fact that the parameters are vectors or matrices is sort of a side point, right? Like really, I could look at them as individual variables if I wanted to, but yeah. Okay. Is there something else I wanted to mention? I forget. Okay, maybe I'll remember. Okay, so if there are no more questions, maybe there are. Now, if we look at, I mean, this is sort of like somewhat cheating. If we look at the perplexity, right? Remember, perplexity basically corresponds to like the training likelihood. Like you run your model on your data, and then you sort of calculate the likelihood you assign to the actual training data that you have. So you see that your language models actually do much better than these word-based trigram models, which again is not surprising because you're running this like stochastic gradient descent with these really fancy neural network type architecture. So you're gonna get better performance usually. Okay, so yeah, so really, okay, so okay, I guess it'll be good to sort of think about. So I mean, I spent a long time talking about the math of this, but remember what we were talking about before when I was talking about sort of the intuition here, right? So in some sense, what we're doing is we're trying to like say, I have some function of the cat is walking, blah, right? So I have some function that then spits out, a sort of R to the V. This basically spits out a distribution over my vocabulary, right? And that's going to basically be this language model, right? So remember, what is a language model? If it's basically saying, given a choice of words, basically that corresponds to the n-1 words that came before it, how do I assign the probability for the next word, right? And obviously I want to assign high probabilities for sentences that make sense, right? So now if we think back, so hopefully now that we've sort of have the model in our mind, this part makes a little bit more sense, because remember what we're doing is we're going to then basically replace these words with vectors, right? So this is going to be like C of the, C of cat, C of is, C of walking, right? So these are just vectors in RV, right? So these are vectors in RV, and the whole point of this is that like, well, I do some transform with these vectors, right? But I'm taking in these vectors and I'm concatenating them. I do some transform that's either a linear transform or nonlinear transform, blah, blah, blah. But the key point is that these transformations are going to be, basically somewhat continuous, right? Almost continuous, actually. I actually don't remember the specifics of this, but it shouldn't change too much, right? And so what that means is that because they're functions of these vectors, these vectors in RV, what that means is that like then if I have like C of kitten, right? C of kitten should be close to C of cat, right? And so then what that means is that the function that sort of that is outputted from this language model basically shouldn't change too much. The output of it shouldn't change too much when I replace kitten with cat, right? Because the function is going to be somewhat continuous, and so this guy then should be close to, well, right? So this guy is then going to look a little bit like that guy. Ah, I cannot draw. Okay, so wait, okay, and also like at the same time, this is sort of how these word embeddings actually end up doing what you want them to do, right? Because your model is trying to basically assign the right probabilities to these things, and it's going to basically pick up on the fact that there are certain words that are basically you can sort of interchange them such that if you put them into the same space, then it's going to be the right likelihood that comes out. So it's sort of like, you can sort of think of it from two ways. Yeah. Okay. Let me just finish off with talking about how we get to word embeddings. Okay, so I sort of hinted at this, and I think this is sort of the surprising thing, which is that like this whole neural language model, the purpose of it was actually to build a language model, right? Language model, again, is something that predicts the next word. What they realized was that actually the best way to build a language model is to have this distributed representation of words, right? Which basically means let's represent words into this high-dimensional vector. That actually means that you can then bypass a lot of the stuff we talked about when we were discussing the sort of the classical language models. Like, if I don't see a particular sentence in my corpus and I don't assign it, if I'm being naive about it, right? So this is a more flexible model that allows you to basically make better language models. Then what they realize is that like, well, these distributed representations are actually useful in their own right? Like somehow the language model was like the original goal, but then they're like, wait, actually the thing we were like creating to create the language model, actually that's even better. And so then what people were going to do is that basically let's try and simplify the language model as much as possible, but then throw as much data as we can into this problem, right? So with this classical neural language model, it's a really slow algorithm because you have nonlinear components, you have a huge bunch of parameters, and so training this like takes forever, right? So what you want is, we talked about this whole issue of big data with these natural language processing type algorithms. The more data these things can see, the more it can sort of suck in data, the better it's going to be. So what they do is to set up word embeddings, I'm going to basically throw away as much as I can about these language models, these neural language models, right? So I'm going to scale back to a bigram model. I'm going to get rid of the nonlinearity. I'm going to do some things I'm going to talk about on Wednesday, sorry. Then this simplifies my computation so much that I can just throw like billions and not trillions, but a huge chunk of data at it, such that it's able to just pick up sort of patterns in the data itself, so that even though the language model now is not as powerful, right, because it doesn't have these, it can't learn as much general functions, because it's feeding in so much data, it actually ends up creating a better embedding that we then now use in all sorts of areas. So that's how we get from, so it's actually a really small step to get from language models to word embeddings. We're going to finish that off to Wednesday. Okay, sorry, went over time a little bit. Yeah, that was pretty intense. I'll be here for questions. Otherwise, ciao. In that, oh no, never mind. That was already a question from before. Okay.
Can I ask something about the homework? But we can also wait if someone else still has other questions first.
Yeah, I mean, I also have office hours, but sure, you can ask a question.
So I guess it's more like clarifying questions. So